compound interest formulas that we had seen before. So let's see, if it just said compound interest, anybody remember what that one was? Starts with an A. P, very good. 1 plus R over N raised to the NT. That was for compound interest, so if they compound quarterly or monthly or something like that, you have to use that formula. It's a little bit more complicated than continuous compound interest. That one was pretty darn easy. It was just PERT, P-E to the RT. Very easy to remember, and we're actually going to use that one in today's assignment. In fact, I'd say more than half of your problems involve that particular formula. And the nice thing is, if you understand how to do this one, then doing the ones that are in section 3.5 on exponential growth and decay are a little bit easier. So over the weekend, I asked you to try and go through and read. I wanted you to read up through the first 3 examples. So let's just quickly go through here and let's talk about this for just a second. This section is on exponential and logistic models. So usually don't say logistic model, you say logistic models. So we've got examples of exponential growth and decay, which we've kind of talked about before. We've used those words. So this right here is an example of exponential growth. Starts small and then kind of goes through that bend area and then just gets steeper and steeper and steeper. This is an example of exponential decay. The models that they used for the 2 of these look like this. Okay, so they've got E, B to the bx. So A is the number out in front. It's like the coefficient. E is the base of the exponential. And then in the exponent, we've got a number we call b. Some books call it k. And then times x. So this is a lot like a equals pe to the rt. We've just got different places here, different variables there. So in place of the p is an a, and in place of the r is a b. So we've got a number here and a number there. The base is the natural number e, and then we've got this variable right there, x. And the difference between the 2 of these, now you'll notice that they say b is positive in both cases, b is greater than 0. I find it a little bit easier to think of it in terms of this. If you've got e to a positive number, it's going to be growth. If you've got e to a negative number, it's going to be decay. I find that a little bit easier to keep track of. They also talked about something called a Gaussian model, which if we had time would be really interesting to go through. We're actually going to cover some statistics and some probability in this class toward the end. You might see that type of model again, so you might want to take a look at that, just briefly. This is called logistic growth. Those are interesting because those model populations much better than exponential growth. If we've got a population of rabbits and say they're confined in a 1-acre pen or something like that, what's going to happen to that population is it's going to grow pretty fast, and then it's going to start to level off because it doesn't have enough food and space and stuff like that. So those are generally a little bit more realistic. And then they've got logarithmic models down here at the bottom. Okay, so that page is just kind of an introduction. Again, the only ones that we're going to deal with are just exponential growth and decay. And we've got a couple different models here. This first example, again, hopefully you read it, was about population increase. Populations usually can be modeled using exponential models, okay? Because they grow a set percentage each year, or at least we can approximate what that is. So they came up with a model right here. So we've got this population that in 1992, and this is in millions. So this is about 5.5 million, or actually, no, this is, if these are in millions, then this would be billions. Holy cow. Yeah, population of the world, yep. So this would be 5.5 billion in 1992. If we come over here to 1990, about 6 billion people in 1990. Anybody know what the population of the planet is right now? A little over 7 billion, okay? So it's going up pretty darn quickly, okay? And it says this right here is a model that approximates this data. Now, the nice thing about this, and you're going to find this in the examples that we do and in the problems that you've got to do for the section, is if they give you the model, that is a huge step. They've already figured out all the math for you. They've given you a function. All you have to do is know what to plug into it or what to set it equal to. Let me say that again. If they give you a model, all you need to know is what do I plug in for the time? What year do I plug in? Okay? Or what do I set it equal to? What population do they want me to find, and when is that going to happen? All right, that's basically the two type of questions that they're going to ask you. Now, you'll notice that on this one, this works for t equals 2 all the way up to 10. So you'll notice our data starts in 1992. This means that this model was probably set so that the year 1990 was 0. So the year 1992 would represent 2. It makes it a little bit easier to plug in the numbers. You don't have to plug in a gigantic number like 1992 or 1995 in order to figure out what the population was then. Okay? So again, they've said that here, t equals 2 represents the year 1992. So then down below, it says, according to this model, when will the world population reach 6.5 billion? So they want to know, when is the population of the planet going to reach 6.5 billion? Remember, I said if they give you the equation, if they give you the function, they're going to ask one of two questions. When will it reach a certain point? Or what is the population at this particular time? So on this one, they want to know when it reaches 6.5 billion. So down here, they went through and they said, here are the actual populations, and here's what the model predicts. And you'll notice that it's pretty darn close. Just compare number to number. Actual population to what the model says. It's pretty close. Here it predicts the population in the year 2000 is going to be 83 million. Get that right? 6 billion here, and then this would be, we'd have a comma there and then all the zeros. Okay? 6,083 million. Okay, right here, the model suggests that the population is going to be 6 million or 6,090 million. Okay? So the model works pretty well. What we want to know is, when does this model equal 6.5 billion? So 6.5 billion would be that. And remember, we're cutting off all of these zeros on the end here. So we want to set it equal to 6,500. So let me zoom in on this for just a second. Let's set this equal to 6,500. And then this is an exponential equation, just like the equations that we learned how to solve in the last couple sections. So if I set it equal to 6,500, I'm now to the point where I need to do some math. I want to solve for what t is. T represents the year that it's going to hit that population. So I divide both sides by 5304. You get this decimal right here. You can write that decimal, or you can leave it as a fraction, 6,500 over 5304. Take the ln of both sides. What does taking the ln do to this problem? Undoes the exponential, right? That's why we just end up with the exponent up here. So that's why we've got the 0.013819t. And then over on this side, this is the ln of that ugly number right there. And then we just divide both sides by 0.013819, and we get this right here. Okay? T equals 14.7. So that's 14.7 years from 1990. So that would be, what did they say here? 2004. A little more than 2004. Actually, probably a little bit closer to 2005. Okay? About halfway through the year. Maybe July or August, somewhere in that neighborhood. Okay? Any questions there? Does that seem relatively easy? Okay. If you flip the page over, and we looked at example number 2, this one's a little bit more complicated. What makes this problem more complicated? It's still about population growth. You have to find the formula, okay? They didn't give us the formula. You've got to find the formula. So the formula for this is, the population is A, e to the bt. That's the model that they're using on this one. Or did they use, I wonder if they used x. Yeah, they used t. It's right there, okay? So they give us two pieces of information. So they say when y equals 100 when t equals 2, and they say y equals 300 when t equals 4. So we can plug those things in. We can put, and they used a y here, I guess, instead of a p for population. So we can plug a 100 in for that, and we can plug a 2 in for t. So we have 100. There's the a, the e, and the b, and then they slid the 2 out in front. We do the same thing on this one. Plug in a 300 here, and plug in a 4 there. So we've got 300 equals a, e to the 4b. And then we start solving this, okay? So on this one, they went ahead and they solved for b, solve for b in the first equation. Oh, to solve for b in the first equation. So they're going to figure out what b is by getting one of them by themselves. So they're going to get the a by itself, and then they're going to take this and they're going to plug it in right there. So this is kind of like solving a systems of equations. If I had x plus y equals 7, and then I had x minus y equals -1, it's like solving that using substitution. It's a little bit more complicated, but it's the same idea. So then they went through and they said, well, 300 equals this stuff right here. They plug that in for a, and you'll notice in this ugly equation right here, we only have the variable b. Everything else is a plain old number. So let's see. How did they get from here, this line right here, to this line right here? Anybody know? Did you look at it long enough to figure it out? Okay, what'd they do? They divided by 100, and what else? E to the 2b. I'll take that. Okay? Might be a little bit easier to see this. There's e to the 2b on the bottom and e to the 4b on top. So if I cancel this with that, that's going to be a 2. So I've got 300 equals e to the 100 e to the 2b. Exponent here is 4b, exponent here is 2b, so I would subtract the bottom exponent from the top, or cancel those off. If I had x to the 3rd over x, I'd cancel this one with one of those, and there'd be 2 left, if you thought about it that way. And then we just divide both sides by 100. Those cancel off. So here's what we've got there. The variable's still up in the exponent, so you take the ln of both sides. Take the ln of both sides. They've canceled this to be a 3. So this would be the ln of 3, and when I take the ln on this side, they didn't show the work, but that's what they did. They took the ln here and the ln there. These undo each other, so you've got a 2b there. So here is what b is. Then you can take that and you can plug it back in and you can find what a is, which is what they did in the next step. And they figured out that a is about 33. Now they're approximating here. It'd be 33.3 repeated. So it might be nice to have a little bit more decimal accuracy. So there's the model right there. Now let me just say this. That number right there, what they found for b and what they found for a, okay, they're approximations. Okay, if we were going to do this a little bit more precisely, we'd maybe carry this out a couple more decimal places, and we'd maybe write 33.33, because 100 over 3 is 33.3 repeated. Okay, so there's going to be a little bit of rounding error there, but for the purposes of this problem, they're saying that's close enough, so I don't mind if you do that. I do think it would be a better idea to be a little bit more accurate. And then it says, since we've got the model, it said, remember what the question was, we did all that work, and here's the question. How many flies will there be after 5 days? We did all of that work right there just to get the model, and look how easy it is to get the answer once you've got the model. Plug in a 5, type it into your calculator, and this predicts there are 514 flies. Not very pleasant, but that's how you do that problem. Now, luckily, I'm not going to ask you to do that on a test. Okay? You just need to be familiar with how these things can be solved and how to use these exponential models. Some of these we're going to go through and we're going to figure out what the model is, but not in that particular way. Okay, so let's talk about carbon dating for just a second. Carbon dating, we're talking about apparently not carbon dating each other, but we're talking about carbon-14 and carbon-12. Now, until I read this book, I didn't realize that they used a ratio of carbon-12 to carbon-14. Everything in your body pretty much is made out of carbon. Okay? All the solid living stuff is made out of carbon. Okay? And that carbon, every living thing has carbon-14 in it. And carbon-14 is slightly radioactive, and it decays. It starts to decay into some non-harmful substance. In fact, carbon-14 isn't even harmful. Okay, but it is slightly radioactive, and it takes a long time for it to decay. So if I had 100 pounds of carbon-14 sitting up here on the desk, and I let about 5,700 years go by, there'd be only 50 pounds left. And if I let another 5,700 years go by, okay, if 50 pounds disappeared in the first 5,700 years, how much would disappear in the second 5,700 years? 25, okay? Seems a little bit counterintuitive. You'd think, well, half of it disappeared here, 50 pounds went away. You'd think the rest of the 50 pounds would go away, but that's not how it works. That's not how half-life works, okay? Another half of it would go away. So we'd be down to 25 pounds and so forth. So would it ever completely disappear? Take a long, long time for that last little tiny atom to disappear, okay? So that's the idea. It kind of follows an exponential decay model, okay? Starts like this, and then just goes down and down and down, hits that horizontal asymptote. So they run through this problem, and they show you how you can find how old something is. So on this right here, it says, let's see, to estimate the age of dead organic material, scientists use the following formula. What's nice about this? They give you the formula, okay, which denotes the ratio of carbon-14 to carbon-12 present at any time t. So they've given us the formula right here. And then it says, you can note that it decreases and all that sort of stuff. The ratio of carbon-14 to carbon-12 in a newly discovered fossil is this ratio right here. It says estimate the age of the fossil. So if that's the ratio, that's what R is. So we set R equal to that. So here's the formula, and we set it equal to that ratio right there, and then we solve. This looks absolutely awful, but let me zoom in on this. If this is what we've got to solve for, if we've got to solve for that t right there, what's the first thing we'd want to do? Talked about this last week. We'd want to isolate the variable term. Here's the term with the variable. So the first thing I'd want to do is I'd want to get rid of dividing by 10 to the 12th. How do you get rid of dividing by 10 to the 12th? Times by 10 to the 12th. Okay? So sometimes this is what makes reading a textbook a little more difficult. You've got to kind of read through the lines to see what step they did. They multiplied by both sides by 10 to the 12th. That leaves the numerator on this side. And then if I have 10 to the 12th on the top and 10 to the 13th on the bottom, I can cancel 12 of those with all but one of those. That's why we have 1/10 on this side. I've still got to solve for that exponential. I'm going to take an ln of both sides to bring that down. So you can see that now we've got just the exponent, negative t over 8223. And that equals the ln of 1/10, which is this number right here. And then how would we finish solving this? Times by negative 83 or 8223. So times by negative 8223. Those would cancel, so I'd end up with t equals, and if you type that into your calculator, that should tell you that it's 18,934 years old. Okay? There's probably some rounding in here. This particular book uses a certain half-life for carbon-14. I've used books that use 5,700, 5,740, 5,600, and stuff like that. Again, we're just kind of trying to get close here. Okay, are there any questions on that one? Okay, good ideas to get in your head, kind of get them cooking. You do need to know how to do those. But we're actually going to just skip the rest of this stuff, and we're going to look at these problems in the textbook. So if you grab your textbook, we're actually going to do some problems. We're going to do some of the problems on your assignment and some that are very much like the ones on your assignment. So here's what we've got here. You've got several problems in this section right here. You'll notice that these don't have anything to do with population or radioactive decay or anything like that. This is just about money. And if you read the instructions, what's the key word in there? Continuous, okay? So it says it changes, this money is compounded, or the interest is compounded continuously. What's the formula then? P to the RT. The amount in the account at any time depends on how much we put in there, the principal, what was the amount to begin with, okay? And then the interest rate times the time. So let's take a look at problem number 8. Okay, it wants us to figure out two things. It wants us to figure out the doubling time, and it wants us to figure out the amount after 10 years. Now, this actually, if you have the model, this is actually the easiest question. Okay, so let's take a look at number 8. On number 8, it says this is the initial investment. What do we usually call the initial investment? P. So they're telling you what P is. So on this problem, A equals 20,000. E, do they tell us the interest rate on this one? Yes, they do. 10.5%. So I want you to put 10.5% right there. Brandon, how do I write 10.5%? Yeah, 0.105. Okay, so 0.015. 0.015. Because if I move this over, whoops, let's see. 10%. Sorry. 105. We'll get this right. So 10.5%, move it over 2 places. 0.105. Doing okay there? Okay. Times T. Okay, here's the model. So if they gave us these two things, they've given us effectively the model. So here's the model. Let's go through and solve this problem now. So let's do this one right here. They want to know how much is present after 10 years. What do? Plug 10 in for T. So this is going to be A equals, so grab your calculator, e to the 0.105 times 10. And you're going to need to use your calculator a lot on these problems. So we've got 20,000 exponential base e, 0.105 times 10. Hit enter. Ooh, that's a lot of money. $57,153.02. Good there? Okay, so that is this answer right here. Okay, now we want to find the doubling time. How long does it take to double? So on this problem, they ask us something different. Remember I said they're either going to tell you to figure out how much there is at a given time, or they're going to say how much time does it take to get to a given value or population or something like that. We want it to double. How much was there in there to begin with? 20,000. So if it doubles, what are we going to get? 40,000. So we're going to set this side equal to 40,000. This side's going to be 20,000, e to the 0.105 t. T is the variable we're looking for. We're looking for the doubling time. How long does it take to double? So to solve this, what do? Divide by 20,000. Okay, now this is kind of interesting what's going to happen here. This will happen every single time. If I take 40,000 and I divide by 20,000, I can cancel those 4 with those 4. And I can cancel the 4 with the 2. So what do I end up over here? I end up with a 2. A 2 because it doubled. If you think about it, it wouldn't matter if I put $1 here and $2 here. When I divide by the 1, I'd get 2 divided by 1. This would be a 2. Or if I put a p here and a 2p here, it's going to take the same amount of time to double no matter what the original amount is because of the interest rate. The interest rate is the same on each one of those. So this is e to the 0.105 t. And then how do I get the t down where I can work with it? ln. So we'll do the ln of 2 equals, this would be 0.105 t, and then I just divide. So t equals ln of 2 divided by 0.105. Grab the calculator and type that in. So ln 2 divided by, make sure you can type these into your calculator and get the right answer. So this says 6.6. 6.6 what? Years, okay? 6.6 years. Now, if it got to 57,000 after 10 years, doesn't it make sense that the answer to get to 40,000 would be a little bit less than that? All right. Any questions? Okay. Take a look at number 10. Okay, if this is P and this is R, if they give us those two things, we've got the formula. They gave us P. Did they give us R? Nope, so we don't have the formula, do we? Do I have enough information that I can figure it out? Yes, I do. Okay, so here's what I do. I put $10,000 in there to begin with, so that's going to be the initial amount. That's going to be the principal. I don't know the interest rate, but I do know that if I plug in 12 years, what would I get out? I'd get out double that. I'd get out 20,000. So if they've told us the doubling time, we can figure out what the interest rate was. And then I'd have the formula. So I'm going to divide both sides by 10,000. Now again, notice what happens here. Those cancel, so I end up with a 2e to the 12r. Just moving it around so it looks a little bit nicer. Always going to be a 2 there because I double. And then I'm going to have the ln of 2 equals 12t. So that means t equals, oops, that should be an r, isn't it? So that means r equals the ln of 2 divided by 12. So let's see what that is. So the ln of 2, I'm just going to recall that, and we're going to divide that by 12. Does that look like an interest rate? Yep. Okay, if we move the decimal over, we'd probably call that 0.577 or 0.0577, okay, which we're going to call 5.77%. So here's the formula, $10,000 to begin with, e to the 0.0577 times t. There's the formula. Could you figure out how much there is after 10 years? What would you do? Plug in a 10, right? Okay, enough of that one. Are there any questions there? Okay, we've got two more finance problems, and then I want to take a look at some of these exponential growth and decay ones. Everybody good there? Okay, so let's take a look at number 16. 16 is not on your assignment, but you've got 15, so it's very similar to, or sorry, yeah, you've got 15, so it's very similar. It says in exercise 15 and 16, determine the principal so that that must be invested at a rate R compounded monthly, so that $500,000 will be available for retirement in T years. So what formula would we use here? It says compounded monthly. A equals P. What's that? Okay, so we've got that. Now this is compounded monthly. If it's compounded monthly, that means n is equal to 12. Here's the time. So I've got n equals 12. Here's the time, and here's the interest rate. So let's plug those things in. How much do we want at the end? 500,000. So there's the A. So we want $500,000. We don't know how much we're investing to begin with, but we do know the interest rate is going to be 12%, so 0.12. Divided by 12 months in a year, we're going to pay interest 12 times per year. And then this is going to be 12 times, what's the time? 40. How many variables in this ugly problem here? Only one. This is just a number. So if I want to get that P by itself, how do I get rid of timesing by this number right here? Just divide by it. So I'd have P equals, I'd have 500,000 on the top. Oops, one too many. Then I divide by 1 plus, this would just be 0.01, wouldn't it? 0.12 divided by 12. Raised to the, is that 480? That'll be a little easier to type into your calculator. Okay? Go ahead and type that into your calculator and see what you get. Are we expecting a number bigger than 500,000 or less than 500,000? Less. A lot less or a little bit less? A lot less, okay? This is going to grow at 12% interest. That's a huge percent interest rate for 40 years. Okay, remember the example we did earlier, maybe a week or so ago, where we put $1,000 in at 8% for 50 years? Even that grew by a ton. This is going to grow by a lot. What number did you get? 4,000? $4,214. Everybody okay with that? Anybody not get that on their calculator? Okay, let's take a look at the next one and pay close attention to this because I want to change the instructions just a little bit. It says, determine the time necessary for $1,000 to double if it's invested at an interest rate of R, compounded. I only want you to do annually, and I want you to do continuously. I want you to make two comparisons. So let's do number 18. Okay, annually would be this. What's N if we pay annually? 1. So this would just be R raised to the N times T, 1 times T. Because if you divide by 1 and times by 1. And continuously would look like this. A equals PE to the RT, right? So we're going to put in $1,000. So this is going to be, this is going to be $1,000. What do we want to have happen to it? Over the time we want it to double. We want it to equal 2,000. And then this is 1 plus, what's the interest rate on number 18? See if I can get this right, 0.105. And what don't we know? We don't know the time. Divide by 1,000 and look at this. There's the 2. There's the 1 plus 0.105 t. And then how do you get the t down where you can work with it? Not divide. What function do we have that allows us to move where the exponent is? Logarithm. Okay? We're going to take an ln. We're going to take an ln of this side and an ln of that side. Remember these problems from last week? So this side is the ln of 2. That's just a number. This allows us to slide the t out in front, and then this is the ln of 1.105. I'll make that look a little bit nicer. That's a number. That's a variable right there, and that's a number. So how do I get rid of timesing by that number right there? Divide both sides by that number. So the answer on this problem is t equals the ln of 2 divided by the ln of 1.105. That will tell you how much time it takes to double. Any questions there? Okay, watch please. I'm going to do this one just slightly differently. If I put in P and I want it to double, what would I put right here? What's double P? What's twice as much as P? Seriously, it's past 8:30. I know it's Monday, but by now your brains have got to be awake. What's double P? 2P. This is 2P. This would be E. What's the interest rate again? 10.5, so 0.105 t. Now this looks like there's more than one variable, doesn't it? But what's the first thing you're going to do to solve? Divide by p. And look what I end up with. 2 equals e to the 0.105 t. Can you finish solving that? I certainly hope so. You're now to the point where you can take an ln. Okay? I'll leave that for you to solve, but that's how you solve those problems right there. Okay? Most of the problems on your assignment are like that. Okay? All right, let's take a look at the next type. I have, I think, 4 more problems that I'd like to do, maybe even 5 if we can get there. Okay? This says complete the table for the radioactive isotope. Okay, these problems, here's how they set these up. They set them up so it's A equals A, E, B to the T. Or let's see, did they do Y? Yeah, we're fine there. Okay? So this is going to be the amount after a certain time. This is the initial amount. In fact, sometimes they'll put a little subscript on there, an A naught, just to represent the initial amount. Okay? There's that growth or decay constant, and because this is radioactive decay, we're expecting this number right here to be negative. Okay? So let's take a look at this problem right here. We've got this Ra-226, so it's some radioactive isotope. Okay? It has a 1620-year half-life. A 1620-year half-life. Here's how you figure these out. If I put in A naught to begin with, if you're more comfortable plugging in a number, if I let a half-life go by, how much is a half-life for this particular substance? 1620 years. If I let a half-life go by, how much of this is going to be left? Half of it, right? 1/2 of A naught. Now, if you're more comfortable plugging in a 10 and letting a half-life go by, what would be the number over on this side? Half of that, so it would be a 5, right? You with me there? Okay, watch how we solve both of these. Divide by A naught, divide by A naught. I get a 1/2 on this side. I get an e to the 1620b. And if I were to solve this one right here, look what I get. Divide by 10, I get a 1/2 e to the 1620b. Aren't these the same equation? How do I get the b? How do I find out what b is? ln. So we're going to do the ln of 1/2 equals the ln of e to the 1620b. What? I'm not done yet. I'm just writing the work. So this is going to be the ln of 1/2 equals, these undo each other, so now I have 1620b. So that means I get a b on this side, and I have the ln of 1/2 over 1620. Okay, now if we did this right, this is decay. What did I say we were expecting for this number right here? A negative. Let's check and see. So if I type this into the calculator, I'm going to do the ln of 1/2 or 0.5 divided by 1620. And there it is. Now, what does this mean right here? I'm not sure we've seen one of these in this class. What does that mean? What type of notation is this? Scientific notation. So B in this case is negative 4.27868 times 10 to the negative 4. So that means we're going to move it over 1, 2, 3, 4 places. So that means B is the number negative 3 zeros, 4, 2, 7, 8. We'll do 7, okay? We'll say that that's close enough. So that's the hardest part. That's the hardest part, is finding that right there. So our formula is the amount equals the initial amount, and then e to the negative 0.004787 times t. Now, we're doing this problem right here. How would I figure out what the initial amount is? Because that's what it wants right there. Okay, if you let how much time go by? If you let 1,000 years go by, this is how much would be left. So I'm going to put a 1.5 here. This is an A naught. This is e to the negative 0.0004277. And then how many years go by? 1,000. So that's going to be 1.5 equals A naught. That's the initial amount, remember. If I times this by 1,000, what's the rule for moving decimals when you times by 1,000? Yeah, 3 places. 1, 2, 3. So here's the number that we've got, negative 0.42787. And then all I need to do is get A naught by itself. So how do I get the A naught by itself? How do I get rid of this right here? Divide by that number, right? So I'm going to divide this side by e to the negative 0.42787. I'll divide this side by e to the negative 0.42787. So I get A naught equals, let's type that into the calculator and see what we get here. 1.5 divided by, now I think it's a good idea to use parentheses on this one, just in case. So this is exponential base e, and then this is negative 0.42787. Started out with about 2.3. Okay. Started out with about 2.3. That's what's going to go right here. 2.3 grams to start with. Okay. Any questions? Okay. Number 28, they give you the half-life. If they give you the half-life in the initial amount, let's talk about how to set that up. If it starts off with 3 grams to begin with, this would be 3 grams. They didn't tell us what this decay constant was. They didn't tell us what tiny little negative decimal that is. But they did tell us the half-life. What is the half-life? How many years go by for the half-life? 5730. And if I let a half-life go by, let's think about this. If I started out with 3 and I let a half-life go by, how much is going to be left? 1.5. Can you solve that for B? And then once you have B, don't you have the equation? And then you can solve the rest. Does that make sense? Okay. Any questions? Okay. Good. Take a look at problem number 36. Just look at it for a second. Is there anything nice about it? It's a story problem, maybe that's no fun, but look at it. Is there anything nice about it? What is it, Hop? Gives you the formula. If they give you the formula, they have done most of the work. Okay? It says T represents the year 2000, and it says, when will the population reach 275,000? So where do I put that? I put that in for P. So I set 275,000 equal to 240,360 e to the 0.012 t. And have we not solved a bunch of these before? Divide by the 240,000. Take the ln of both sides to bring that down where you can work with it, and then divide by 0.12, and that'll give you your answer. Okay? Any questions? Okay, I don't think we need to finish this. We've solved a bunch of those like that already. Take a look at problem number 37. 37 is on your assignment, so let's take a good glance here. The population of a city P is population P of a city is represented by this right here. Okay, what's good and bad about this? Okay, did they give us the whole equation? No. Did they give us part of it? They did give us part of it. Okay? So it says year 0 represents 2000. In 1945, the population was 1,350. Find the value of k and use the result to predict the population. So if I went back in time, how far? If 0 represents the year 2000, that'd be negative 55 years, wouldn't it? So it was 1350 negative 55 years ago, or 55 years ago. So we've got 1350 equals 2500 e to the negative 55k. Can you solve that? Okay. That one's on your assignment, by the way. Okay. Let's take a look at number 38. And I'm recording this. I'll post it so you can watch this again if you need to. Didn't give us the whole formula, but it does say that in 1960 the population was 100,250. Is there any difference between this problem and the one before? Just that this is going to represent a t of negative 40 years. Okay? So there was only 100,250. Whoops. Negative 40 years ago. Once you find the k, would you have the whole problem, the whole formula? And then they want to know, find the population in the year 2020. Once you get the formula, what are you going to do with it? What t would the year 2020 represent? T equals 20. So, find formula. Okay. In other words, find out what k is. Plug in t equals 20. Okay? Last one. Take a look at that one. Does that look familiar at all? RA 226, half-life of 1620 years. Let's slide this back up here. Number 26. What did we figure out on this one right here? Could you figure out what B is? That number right there is the same B, the same constant that you'd use up. Well, let's see. Oh, we did figure it out right here, didn't we? This is it right here. Let's see, what percent is present after 100 years? Let's say there's 100% to begin with. And then what did we figure out the k was? Negative 0.000428787. Is that right? T equals A. And they're just saying, what percent would be left after 100 years? What would I plug into this? Plug in 100. That'll tell you what the percent is, especially because we set it up with 100% present initially. Okay? All right. Please come tomorrow with questions on 3.5 and the review. I will post the review. Please make sure you look, and I'll email it. Okay? If you don't see an email from me by noon, send me an email so I know you've got it.